Bonjour, welcome to Wahsa Distance Education Center's radio Zoom classes. This is MBF3C, grade 11 college math, and I'm the teacher, Bronwyn Slate. If you'd like to participate live today, you can call the Wahsa studio at 1-800-465-7144 or 737-4017. You can listen on the radio at 91.9 FM and also on the television at Bell Expressview channel 972. You're always welcome to join me live through the Zoom link, which is available both from me, your teacher, and also your DEC. Our radio Zoom schedule is such that we have classes on Monday through Thursday, and they run from 2 till 3 in the afternoon. We are in our second week of our 9-week course. So a reminder of what work to submit for marking once you are ready to. The support questions, the ones with the little pencil icon, are not for marking. You decide which ones and how many to do. If you need to do them all, totally fine. If you need more and you need some extra practice, ask me. I'm happy to give you more practice. If you're understanding a concept and you don't feel like you need to do more and it's just wasting your time, feel free to skip questions and only do the ones that you feel like are going to be challenging for you. The answers are in the back of your booklet, so please check your work. This really helps you to figure out if you're on the right track or if you are confused or having a hard time. So please check your work in the back. The key questions, the ones with the little key icon, sorry, are the marked questions. So please do all of them, showing all of your work, your steps, your thinking. This way I will get the best understanding of what it is that you understand. And if you're struggling with something, I have more information in order to figure out how I can support you. So how do you actually submit your work for marking? There's 3 methods. The first method is to scan your work and send it electronically. You can scan your completed work using a device. If you have an Apple device, the Notes app has a scan function. And if you have an Android device, the Google Drive app has a scan function. Both these apps are free and generally come with these devices. But you can, again, download them for free if you need to. In my YouTube channel, I have a couple of videos under my tech tutorials that show you how to actually use these to scan. So feel free to check those out if you need help or ask, and I'm happy to walk you through it. Then you can send it through email to studentwork@nnec.on.ca and CC it to bronwyn.slate@nnec.on.ca. Or you can also send it to me through Facebook Messenger, where my name is B. Slate Wahsa. The second method is to drop your work off in Sioux Lookout. We have an outdoor mailbox at our 74 Front Street location. We're the bright red building, and we have a small white mailbox next to our side entrance. The third method is to hand your work into your DEC. Your DEC can either send your work through the Express or fax it to 807-737-1732 or toll-free fax to 1-800-463-7852. If you'd like to connect with me through social media, it's a great way to communicate and also to access our radio Zoom classes. Both my Facebook and my YouTube channel are under the name B. Slate Wahsa. So you can friend me on Facebook or subscribe to my YouTube channel and you'll get notifications every time I upload one of our videos. All of our radio Zoom classes are recorded and I post them to YouTube shortly after airing. There's also short videos that explain common errors or confusing concepts on my YouTube channel. And so this is a good place to go if you are struggling with something, if you're unsure about something. Checking out my channel first before just doing a general internet search can maybe hopefully help you without having to do a lot of work finding the information. Math is a really visual subject, so I strongly encourage you to access the videos. If you're only listening, you will only get a small portion of what it is that I am teaching. So really try to check out the videos. If you can't join me live through Zoom and you can't access the YouTube videos, you don't have reliable internet or something like that, then let me know and I'm happy to send you a copy of the videos so that you'll still get the full experience. All right, if you have any questions or concerns, please reach out and connect with me. I am here to support you however I can. You can email me at bronwyn.slate, and that's spelled BRONWYN.SLATE@nnec.on.ca. You can connect with me on Facebook at Wahsa. You can call me at 807-737-1488. My extension is 2209. Or you can also call the office toll free at 1-800-667-3703. My office hours are Monday through Friday, 9 a.m. to 3 p.m., though I teach the last hour of my day, so that's not a great time to try to get a hold of me. All right, we are continuing with lesson 4 today, the second part of the exponent law lesson. So a reminder that our learning goals for this lesson is that you'll be comfortable calculating simple powers and you'll understand the logic behind the exponent rules. You know you've met these learning goals because you could execute with comfort the multiplication, division, and power of power rules, which is what we focused on in our last video, in our last class. Or you can, and then number 2, you can explain the reasoning behind zero and negative exponents, and that's what we're focusing today's lesson on. But first, let's activate your brain with some mental math. I don't believe in mad math minutes. They do not set folks up for success or give them the tools that they can use in various places in their lives. They just focus on speed and memorization. So instead, we work on developing skills in my class that develop comfort and ease with numbers and confidence. So you can actually apply what it is that you know and feel comfortable with it. Today's question is 72 divided by 4. And we are using the strategy of multiplying up. So division is something that many folks struggle with. Long division, just trying to memorize the steps, doesn't really work. So this strategy is to kind of ignore division and think about the inverse. So instead of thinking of 72 groups, 72 things, dividing them into 4 groups, we're going to think that if we have 4 groups of how many things is going to get us up to 72. So to me, 72 is really close to 80, I can see. And I know that if I have 4 groups of 20 things, then that's going to be 80, because 4 times 20 is 80. But I know that that is too much. So I can try to think of something smaller, or I can look to see if I can see any other connections in between my numbers. So 80 is really close to 72. It's actually only 8 away. So that just means that I need 2 less things in my group. If I want to take away 8, I don't want to take away 2 whole groups of 20 things, because then I will only have 2 groups of 20 things, and that's going to be 40. But if I want to take away 8 to get to me 72, that means that I need to take 1 thing away of each of my 4 groups. I need to take 2 things away from each of my 4 groups. So really, if I have 4 groups of 18 things, that is going to give me 72. So 72 divided by 4 is 18. So that's another way of thinking about division. All right, mine's on. Let's do a little bit of review from our last lesson just before we dive into today's, because today's are tricky and we'll need some of yesterday's to help our last lessons to help us. So a reminder of what exponents, how they work. Remember, the base, the number at the bottom is the big number at the bottom is called the base, and this is the number that we will be multiplying. The exponent is the little number that is a superscript that is up to the top, is shifted up, and the small to the top right. and this whole thing is called the power, and that's one unit. It's one thing. The base and the exponent, they have separate roles, but they're one thing. If you take the base and the exponent as two separate things, then they are something completely different. They're not this power anymore. So you need to remember that they're one unit that have two parts to explain what you're doing. So the exponent states how many times the base value is being multiplied by itself. So if, for example, if we have our blue circle to the exponent 5, that means we have blue circle times blue circle times blue circle times blue circle times blue circle. So we did that 5 times. And that's why you can't just take the exponent number away and apply it to something else, because the 5 is meaning how many times we're multiplying the blue circle by itself. All right, so from our previous lesson, the exponent laws part 1, we remember that we're always talking about things with the same base. We talked about why that was important and how when we're applying these rules, these numbers and letters have to have the same base. So either are the same number or the same variable, otherwise it doesn't make sense. If we're multiplying power rules, the multiplying rule is that we add the exponents. So if we have a power times a power where the base is the same, we add those two exponents. The base stays the same and we add the exponents. So x to the exponent a times x to the exponent b is equal to x to the exponent a plus b. If the dividing powers rule is if we have the same powers, sorry, the same base of the powers, then we subtract the exponents. So b to the exponent x divided by b to the exponent y is equal to b to the exponent x minus y. Then the power to a power rule means that we multiply the exponents. So t to the exponent n all to the exponent p is equal to t to the exponent n times p. All right, so let's dive into what is new today, where we'll be focusing on zero exponents and negative exponents. These are two things that our folks really struggle with and really have a hard time, find very confusing. They are a little bit tricky, but hopefully we will be able to figure it out. We're going to be looking at two different methods for each of these exponents rules. They're two different methods for understanding why they happen. What actually happens is the same. They're just two different methods to understand, to justify it, to understand what is going on. So first, we're going to do a looking at the pattern method for 0 as your exponent. So we're going to use the example y equals 2 to the exponent x to figure out what happens when we have 2 to the exponent 0. That's our goal. So this is just an example. So we're going to use a table of values, and we're going to start with 5 as our x. So y is equal to 2 to the exponent 5. So that means that we have 2 times 2 times 2 times 2 times 2, which is equal to 32. Then if x is 4, so that means y is 2 to the exponent 4, which is 2 times 2 times 2 times 2, which equals 16. Then x equals 3, y equals 2 to the exponent 3, and that equals 2 times 2 times 2, which is equal to 8. Then we have 2 as our x, so y equals 2 to the exponent 2, which is 2 times 2, which is equal to 4. Then we have 1 as our x, so 2 to the exponent 1 is equal to 2, which is equal to 2. And now we have 0 as our x, and now, so y is equal to 2 to the exponent 0, and now we don't really know what that could make any sense, like what that's going to be. So we're going to look at the pattern that we've already created, because we're just going down by one step each time with our x. So we're going to look to see what pattern is happening between those numbers. So when we increase our x value, so our exponent value, we are multiplying by 1 more 2. So our constant ratio is 2, right? So as x gets bigger, we went from 1 to 2, we multiplied by one more 2. We're going from 2 to 3. We went from 2 times 2 to 2 times 2 times 2. We multiplied it by one more 2. From 3 to x equals 3 to x equals 4, we multiplied by one more 2, right? Every time we increase our x value, we're multiplying by one more 2. So that means that our constant ratio is 2. We're multiplying by the same number, and that's 2. That's what constant ratio means. So if we then go backwards, and it means that if we divide the previous term by 2, we'll find the next term. So if we do, so x equals 5, y equals 32. When x equals 4, if we do 32 divided by 2, we get 16. And then if we're going down to x equals 3, if we do 16 divided by 2, we get 8, which is what y equals. When x equals 2, we do 8 divided by 2, and that gives us 4, which is what y equals. When x equals 1, we do 4 divided by 2, and we get 2, which is what y equals in that case. So the same thing, if we do the same pattern, and we think that we take the previous term and we divide it by our constant ratio, our 2, then we get 2 divided by 2, which is equal to 1. So when x equals 0, when we have 2 to the exponent 0, that equals 1 if we look at this pattern of where we constantly were dividing by the previous term by the constant ratio. So 2 to the 0 is equal to 1 in this example. Okay. So that is interesting. So let's look at another example to see what happens if we change our number. So this time we're going to do, our example is going to be y to the equals 5 to the exponent x. So we changed our base to 5. And we're still going to do the same thing. We're going to use our t-chart and we're going to do our table of values. So if x is equal to 3, y is equal to 5 to the exponent 3, which is 5 times 5 times 5, which is 125. When x is equal to 2, we have y to the exponent 2, which is equal to 5 times 5, which equals 25. When x is equal to 1, we have y equals 5 to the exponent 1, which is 5, which is 5. Then when x is equal to 0, we have 5 to the exponent 0. And again, we're not sure what this is going to equal. But the same thing's happening. As our x increases, we're multiplying by one more 5. So this time our constant ratio is 5 because our base is 5. We're increasing by that number one more time. That's the definition of exponents. So we can, again, divide the previous term by 5 to find the next term. So 125 divided by 5 gives us 25. So we went from when x is equal to 3 to x is equal to 2. When x is equal to 1, we look at x is equal to 2, 25 divided by 5, and we have 5. This one's tricky because we have a lot of 5s. That's the joy of 5. So then if we do 5 divided by 5 to go from when x is equal to 1 to x is equal to 0, well, 5 divided by 5 is equal to 1. So that means that x to the 0, when we have y equals 5 to the exponent 0, that is equal to 1. So again, we have 5 to the exponent 0 is equal to 1. Okay, that's the same as what we had last time. So let's look at this in general, and let's do it instead of having a number as our base. Let's use we're going to use just the letter b for base. So looking at our table of values, if we have x is equal to 5, then y is equal to b to the exponent 5, because we have b times b times b times b times b, which is b to the exponent 5. We can't simplify it anymore because we have a variable. So when x is equal to 4, y is equal to b to the exponent 4, which is b times b times b times b, which is b to the exponent 4. When x is equal to 3, we have b to the exponent 3, which is equal to b times b times b, which is equal to b to the exponent 3. When x is equal to 2, we have b to the exponent 2, which is equal to b times b, which is equal to b squared, b to the exponent 2. When x is equal to 1, we have b to the exponent 1, which is b, which is b to the exponent 1, b. It's the same thing. So when x is to the exponent, when x is equal to 0, y is equal to b to the exponent 0. Again, let's look. This time when we're increasing the x value, our exponent value, we're multiplying by 1 more b, where our constant ratio is b, right? That's what the base is defined by. So if we divide our previous term by b, we'll find the next term. So b to the 5th divided by b is equal to b to the 4th. Yep, that's what we got. B to the 4th divided by b is equal to b to the 3rd. Yep, that's the next term. B to the 3rd divided by b is equal to b to the squared. B to the 2. Yep. B squared divided by b is equal to b to the 1. So that means that b1 divided by b is equal to 1, because b divided by b is 1. Doesn't matter what the numbers are. If we take any number and we divide it by itself, it's always going to be 1. So b to the exponent 0 is equal to 1. Always, no matter what we do, b to the exponent 0, any number to the exponent 0 is always going to equal 1, no matter what, always and forever. This is key. This is the rule. All right, so now we're going to look at another method to see, because today's rules are really confusing for many folks. So we're going to look at different ways. If that way makes sense to you and this method too is confusing to you, don't worry about it. This is just so that you understand. The goal of these methods is so that you understand the rule and can apply the rule. If they both make sense to you, great. If neither one makes sense to you, reach out to me and let's talk about it. Let's try to figure it out together. Okay? If only one of them makes sense to you, that's totally fine. It's okay. You don't need to understand them both as long as you understand one of them. So we're going to use the division rule. So this is how it's explained in your workbook on page 27 in your IEL booklet. So we're going to use the example of 7 to the exponent 2 divided by 7 to the exponent 2. So 7 to the exponent 2 is equal to 7 times 7 divided by 7 times 7. And that means that we can cancel off 7 and 7 and 7 and 7, right? Because if we're multiplying by a number and dividing by a number, then they cancel off. So we end up with 1 divided by 1, which is equal to 1, which makes sense. If we have 7 squared divided by 7 squared, we have the same thing on the top and the bottom, or the same thing that we're dividing. We're dividing a number by itself, which means, of course, we're getting 1. We have a whole. That's a primary definition. But if we think about the division rule that we learned in our last lesson, the shortcut, remember, is that if we're dividing by something with the same base, then we can subtract our exponents. So 7 to the exponent 2 divided by 7 to the exponent 2 is equal to 7 to the exponent 2 take away 2, which is equal to 7 to the exponent 0. So again, we get it so that 7 to the exponent 0 is equal to 1. So let's look to see if we are using a variable. Does this change in any way? So we're going to use the example t to the exponent 8 divided by t to the exponent 8, which is equal to t times 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 t divided by t times 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 t. So we've got 8 t's on the top and 8 t's on the bottom. So that means that they each cancel each other out and divide by to be equal to 1, right? They just, because we're doing the same thing on the top as the bottom, we have a whole. So we still end up with 1 divided by 1, which is equal to 1. So if we look at our division method shortcut, t to the exponent 8 divided by t to the exponent 8 is equal to t to the exponent 8 take away 8, right? Because that's our division rule for dividing by the numbers of the same base. We can subtract the exponents. So we have t to the exponent 0. So again, it doesn't matter what our number is, that has no relevance to it. T to the exponent 0 is equal to 1. Any number to the exponent 0 is always going to equal 1. The exponent doesn't become 1. No, the answer becomes 1. Any number to the exponent 0 is always going to equal 1. Try it on your calculator. Put in any number to the exponent 0, it's going to be 1. So just to reiterate, because this people, yes, the exponent rule is anything with an exponent of 0 equals 1. Except 0 to the exponent 0. That can't be solved because we can't divide by 0. So that doesn't make any sense. So the only disclaimer is that 0 to the exponent 0 cannot be solved. It doesn't make any sense. Okay. So let's do some practice questions. We're going to evaluate these numbers. So we have part A, 25 to the exponent 0. So we're going to do it on my calculator just so that you believe me. 25 to the exponent 0 is equal to 1. Now we're going to do negative 3,726 to the exponent 0 is equal to 1. Then we are going to do 1 million to the exponent 0 times 1, 2, 3, 4, 5, 6, 7, 8, 9 to the exponent 0, and it equals 1. So again, anything to the exponent 0 is equal to 1. Doesn't matter how complicated you make it, it equals 1 if you raise it to the exponent 0. If we simplify our, we have variable p to the exponent 0 is equal to 1. Negative q to the exponent 0 is equal to 1. Here I have s to the exponent 7 times s to the exponent 3 divided by s to the exponent 10. So I have s, I think of my other rules, I have 7 plus 3 because I'm multiplying those, minus 10 because I'm dividing. So s is going to be 7 plus 3 is 10. Take away 10, so that's going to be s to the exponent 0 is going to equal 1. Okay, no matter what, anything to the exponent 0 is always equaling 1. Okay, so that is 0 exponents. Now let's look at negative number exponents. Negatives people don't like, exponents people don't like, so this is a hard one, okay? Again, we're going to look at the pattern like we did with the negative, or with the 0 exponent. We're going to look at a pattern first, and then we're going to look at a division method. So we're going to, for this pattern method, we're going to use the example y equals 3 to the exponent x. And we're going to do the same thing that we did before. We have a table of values, and we're going to say 3 is x. So that means that 3 to the exponent 3 is equal to 3 times 3 times 3, which is equal to 27. 2 to the exponent, x is equal to 2. So we have y is equal to 3 to the exponent 2, which is equal to 3 times 3, which is equal to 9. Then we have x is equal to 1. So we have y is equal to 3 to the exponent 1, which is equal to 3, which is equal to 3. Then we have x to the exponent 0. X is equal to 0. So we have 3 to the exponent 0 is our y. And we know that that is equal to 1. But now we have, as we're continuing our pattern of x's, we're going down by 1 value. Now we have negative 1. So we have x to the exponent negative 1. What does that equal? Well, we can do the same thing, right? The same thing is true, that when we increase our x value, we are multiplying by 1 more 3. So our constant ratio is 3. So we can still, if we divide the previous term by 3, we will find the next term. This pattern still applies in both of these situations. It's the same thing. So if we do 27 divided by 3, we get 9, which is our next term. We do 9 divided by 3, we get 3, which is our next term. We do 3 divided by 3, we get 1, which is our next term. So then if we do, to find our next term, if we do 1 divided by 3, we get 1 over 3. We get the fraction 1 divided by 3. 3 is the same as 3 to the exponent 1. So what 3 to the negative 1, to the exponent negative 1 is equal to is 1 over 3 to the exponent 1. Okay, so if we do x is equal to negative 2, let's keep going because this is still confusing. So we have y is equal to 3 to the exponent negative 2. So we want to do our previous term, 1 divided by 3 divided by 3. So that means that we have 1 divided by 3 times 3 because we're divided by 3 twice. So that's equal to 1 divided by 3 squared. So 1 over 3 to the exponent 2. So 3 to the negative 2 is equal to 1 over 3 to the positive 2. So let's just do one more. If x is equal to negative 3, so then y is equal to 3 to the exponent negative 3. So if we divide our previous term, 1 divided by 3 to the exponent 2 divided by 3 means that we have 1 divided by 3 times 3 times 3 because we're dividing by 3 times. So we have 1 divided by 3 to the exponent 3, which means that 3 to the exponent negative 3 is equal to 1 divided by 3 to the exponent positive 3. So we can see that whenever we have a negative exponent, we do the reciprocal, is what it's called. We do 1 over that number to the positive exponent. So our exponent number stays the same, but it goes from being negative when it was in the exponent to when we flip it into be a fraction to be positive. This one people really, really struggle with. This one's really hard. So let's look at another example. So this time we're going to do y equals 6 to the exponent x. In our table of values, we're going to do 5 as our x. So 6 to the exponent 5 is equal to 6 times 6 times 6 times 6 times 6, which is 7,776. Not one that I know in my head. X is equal to 4, y equals 6 to the exponent 4, which is 6 times 6 times 6 times 6, which is 1,296. X to the exponent 3, x is equal to 3 is y means 6 to the exponent 3, which is 6 times 6 times 6, which is 216. Then we have x equals 2, so we have 6 to the exponent 2, which is equal to 6 times 6, which is equal to 36. Then we have 1, x to the exponent 1 is equal to 6, which is equal to 6. We have x equals 0, 6 to the exponent 0, which is 1, because we've now learned that it's always equal to 1. So we have, looking at 1 x equals negative 1, what does 6 to the exponent negative 1 mean? Well, we have a constant ratio of 6, right? So that means that if we divide the previous term by 6, we will find the next term. So let's try. So 7,776 divided by 6 gives us 1,296. 1,296 divided by 6, it gives us 216. 216 divided by 6 gives us 36. 36 divided by 6 gives us 6. 6 divided by 6 gives us 1. So we are following this pattern. That means that to get to our next term, we do 1 divided by 6. So we have 1 over 6, because 1 divided by 6. So 1 divided by 6 to the exponent 1 is what 6 to the exponent negative 1 is equal to. So if we have negative 2 to the exponent, x equals negative 2, so we have 6 to the exponent negative 2. This is why looking at it is really super important, because it's easy to twist it up in your words. So if we have 1 divided by 6 to the exponent 1 divided by 6 is the same as 1 divided by 6 times 6, because we're dividing by 6 twice, which is equal to 1 divided by 6 to the exponent 2. So 6 to the exponent negative 2 is equal to 1 over 6 to the exponent 2. If we do negative 3, so 6 to the exponent negative 3, we divide 1 over 6 squared divided by 3, divided by 6 is equal to 1 divided by 6 times 6 times 6, because we're dividing by 6 3 times. So 1 over 6 to the third. So 6 to the exponent negative 3 is equal to 1 divided by 6 to the exponent 3. And one last one, if we have negative 4, so 6 to the exponent negative 4, that means that we have 1 over 6 to the exponent 3 divided by 6 is equal to 1 divided by 6 times 6 times 6 times 6, because we're dividing by 6 4 times, which is equal to 1 over 6 to the exponent 4. So 6 to the exponent negative 4 is equal to 1 divided by 6 to the 4th. So again, this number 6 to the exponent, 6 to the exponent negative x is equal to 1 divided by 6 to positive x. So again, let's look at this with a variable. B to the exponent 3 is equal to b times b times b. B to the exponent 2 is equal to b times b. B to the exponent 1 is equal to b. B to the exponent 0 is equal to 1. That we should be all comfortable with. So b to the exponent negative 1, this time we have a constant ratio of b. So if we divide the previous term by b, we will find the next term. Same. So b third divided by b gives us b squared. Yes. B squared divided by b is equal to b. Yes. B divided by b is equal to 1. Yes. 1 divided by b is equal to 1 over b, which is the same as 1 over b to the exponent 1. So b to the exponent negative 1 is equal to 1 over b to the exponent 1. So b to the exponent negative 2 is equal to 1 divided by 1 over b to the exponent 1 divided by b, which is equal to 1 over b times b, which is equal to 1 over b squared. So b to the negative 2 is equal to 1 over b to the positive 2. B to the negative 3, so we do the previous term, 1 over b to the positive 2 divided by b is equal to 1 divided by b times b times b. So 1 over b to the exponent 3. So b to the exponent negative 3 is equal to 1 over b to the exponent 3. So it doesn't matter what the variable or what the base is. Any number to the exponent negative something is equal to 1 over that base to that positive exponent. This one is people have a really hard time with. So let's look at method 2 using division. So we're going to use a number example where we have 4 to the exponent 3 divided by 4 to the exponent 9. So we have 4 times 4 times 4 divided by 4 times 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 4. And we're going to cancel off the 4s. We're going to cancel off as many 4s that we can from the top and the bottom. When we run out of 4s at one time, at either the top or the bottom, then we can't cancel off any more 4s. So we're left with, we cancel off 3 because we have 3 on the top. We're left with 1 over 4 times 4 times 4 times 4 times 4 times 4, which was 6 4s. So we have 1 over 4 to the exponent 6. So then we think of our shortcut with our division method. We know that 4 to the exponent 3 divided by 4 to the exponent 9 is equal to 4 to the exponent 3 take away 9, which is 4 to the exponent negative 6. So 4 to the exponent negative 6 equal to 1 over 4 to the exponent positive 6. Looking at a variable example, we have w to the exponent 4 divided by w to the exponent 6. So we have w times w times w times w times w divided by w times w times w times w times w times w times, oh, that was the last one, sorry, 6 w's. So we, again, cancel off as many as we can. We have 4 on the top, so that's as many as we can cancel off. So we have 1 over w times w, which is 2 w's. So we have 1 over w squared. With our shortcut method, we have w to the exponent 4 divided by w to the exponent 6, which is equal to w to the exponent 4 take away 6, which is equal to w to the exponent negative 2. So again, doesn't matter what our base is, w to the exponent negative 2 is going to be equal to 1 over w squared. So our negative exponent rule is that a negative exponent equals the reciprocal of the base. So 1 over the base, which includes the base. You then also have the exponent of the on the base as well. The exponent doesn't go away. The number is still there. Okay, so a few tricky examples before we do some practice. Probably should have done the practice first, but anyway. If we have 1 over 2 to the negative 10, so we already have it in a fraction. We already have it 1 over something, but then we have a negative exponent in the denominator in the bottom. We still flip the fraction, so now we have 2 to the exponent 10 over 1. So that means that really we just have 2 to the exponent 10. Do you see that here when I flipped it, my exponent became positive? So even though it's not in the denominator anymore, because I flipped it, the negative means that I flip. Once I flip it, I end up with a positive. Okay, super important. If I have a fraction where I have 7 over 8 to the exponent negative 4, so I don't have 1 over anything, this means how you can think about it is that, so we have the negative 4 is applied to both the 7 and the 8. So we have 7 to the negative 4 over 8 to the negative 4. So we're going to flip them both. We're going to end up with 8 to the exponent 4 over 7 to the exponent 4. So because they're both negative, we flip them both, which means that when we're flipping them, the denominator becomes the top and the numerator becomes the bottom, and the 4 still applies to both. So those ones can be extra tricky. This is already hard, but those ones can be extra tricky. Okay, so let's do some practice. So first, let's evaluate. Let's see what happens when we actually evaluate these. So if we have 4 to the exponent negative 3, so we end up with 0.015625, which is a decimal, which is 1 over 64, which if you do 4 to the exponent 3, you'll get 64. So 1 over 64. You can do it either in a fraction or a decimal. Doesn't matter. Okay, another one that people really struggle with is if you have a negative base. If we have negative base and we have a negative exponent, these are two completely different things. They don't cancel each other out or anything. You need to think of them as the two separate things. They have separate meanings. So negative 8 to the exponent negative 4 is equal to, let's put it in a fraction, 1 over 4,096. And here I have 3 over 4 all to the exponent negative 2. So that means if I'm evaluating it, I have 3 divided by 4. Sorry, anyway, whatever. 3 divided by 4 all to the exponent negative 2. Oh, wrong button. is equal to 1.77777, which is equal to 16 over 9. So you can see that we did 4 to the exponent 2 over 3 to the exponent 2. We flipped it and then we squared them both. So if we're doing this with just variables, so we have d is equal to d to the negative 10 is equal to 1 over d to the 10. Here we have negative e to the exponent negative 3. So we have 1 over negative e to the exponent 3. Here I have j divided by negative 2 times negative 5. So that means that I have j to the exponent 6 divided by j to the exponent negative 2 times j to the exponent negative 5. Sorry, I didn't say that right properly first the time. Okay, so we have j the exponent 6 take away negative 2 plus negative 5 is equal to, so j6 take away negative 2 is 8 plus negative 5 is negative, is 3. So you can end up with positive even if you have negatives. It's very possible that they're going to be up there to confuse you. It's going to happen. Okay, so now you can do the support questions from page 28. And now you can do questions 1A, C through G, and then 2A, C, E, and F. You can really do all questions of 1 and 2 if you've done both parts of these lessons now. Just these are the ones that include 0 and negative exponents, and you weren't ready to do those after the end of last lesson. All right, so we have a few minutes to do some practice problems. So a reminder that knowing what the question is asking for, if it's asking to evaluate, it's asking you to calculate a final answer, you should have a number of some sort. If you're asking to simplify, you're combining the exponents as much as possible, and also you do not want to have any negative exponents. So simplifying means you want to end up with a positive exponent. All right, so we can go through and evaluate these on a calculator, but you can do that on your own. I trust that you can actually do that. Remember, your calculator buttons might look different than how it looks on my Desmos, so check that out. But let's do some practicing with some simplifying because these can be confusing. So part A, we have 4 to the exponent 12 times 4 to the exponent negative 3 divided by 4 to the exponent negative 9. So these totally can be awkward, but first, do they have the same base? Yes. So that means that we can combine the exponents. So then I have 4 to the exponent 12, and then I have times. So that means that because I'm timesing, multiplying, I'm going to add my exponents. And then I have my exponent is negative 3. So that means I'm going to have a negative. So I'm adding negative 3. And then I'm dividing. So I'm going to subtract. And I'm dividing. My exponent is negative 9. So I'm going to have negative 9. It is best to combine your exponents first and then if you have a negative, then turn it into positive. It'll just make your life a little potentially easier. So 4 is my base. So 12 plus negative 3. Well, 12 take away 3 is 9. So then I have 9 minus negative 9. So that's going to be 9 plus 9, which is 18. So that is equal to 4 to the exponent 18. And then we're done. We simplified as much as we can. All right, so here I have part B. I have 9 to the exponent 9 divided by 9 to the exponent 4 divided by 9 to the exponent negative 2 divided by 9 to the exponent 0 times 1 over 9 to the exponent negative 3 all to the exponent 6. So these sometimes your questions will be really confusing and convoluted like this, just to get you to practice and to making sure you're paying close attention. So with this sort of thing, I would deal with them and simplify them as much as I can. So I would think of each of my terms. So I would think of this and simplify that. And then I would simplify this, and then I would simplify this, and then I would deal with them across. So that's just how I would do it. You don't have to do it the same way as me. You can do it in a way that makes sense for you, but that's what makes sense to me. So here I have Actually, I'm going to write it underneath here to help keep myself organized. So 9 to the exponent 9 divided by 9 to the exponent 4. So that means I have 9 to the exponent 9 take away 4 is my first term. Divided by, I'm going to leave that divided by there. And then I have 9 to the negative 2 divided by 9 to the 0. So 9 to the 0 is just 1. So that's just going to be, this is just 1. So that's just going to be 9 to the negative 2. Don't forget your negatives. Okay. And then times 1 over 9 to the negative 3. Well, that just is going to be 9 to the exponent 3 because my negative means I need to flip it and it's 1 over. And then all to the 6. Okay, so now I'm going to simplify. So now I have 9. 9 minus 4 is 5. And then divided by means I'm going to subtract negative 2. Okay, and then times, and then 9 to the exponent 3 times 6 because I have 9 to the exponent 3 all to the exponent 6. So I'm power rule there. So then I have 9 to the exponent, well, 5 take away negative 2 is 7. And then I'm adding because I'm multiplying the 2. And then 9 to the exponent 3 times 6 is 18. So this in total is going to equal 9 to the exponent 7 plus 18 is 25. And there we go. So breaking it down to steps that make sense to you is really important. All right, we are going to do, I'm going to skip C because we don't have time, but I'm going to jump to part D. And I have 5 to the exponent A divided by 5 to the exponent B times 5 to the exponent A. So with this one, when I have variables in my exponents, I just need to apply the rule. So 5 to the exponent A divided by 5 to the exponent B is A take away B plus times 5 to the exponent A means that we're adding because we're multiplying there. So we have 5 to the exponent A take away B plus A is equal to 5 to the exponent, well, A plus A is 2A take away B. And so that's what you do when you have exponents in your variables in your exponents. And let's do one more. We're going to do part B on this one. So we have 11 to the exponent 2B minus A divided by 11B divided by 11C to the exponent C plus B. So we have 11 2B minus A for the first one divided by, so that means I'm going to subtract my exponents, B, then divided by again. So I'm going to subtract my exponents, C plus B. It's really important to remember that I'm subtracting that whole exponent. So I have 11 2B take away A, well, take away B, take away C, take away B. So I have 11. Well, I have 2B, take away B, take away B. So the B's cancel out. So I have 11 to the exponent A, negative A, take away C. So again, can be awkward. You just got to work through it. All right, so let's quickly consolidate before we, in our last minute. So remember, we're always talking about the same base. Multiplying power rules, we add the exponents. When we're dividing, we subtract the exponents. When we have a power to the power, we multiply our exponents. And then today's new ones, anything with an exponent of 0 equals 1. So t to the exponent 0 is equal to 1. And if we have a negative exponent, it means that it equals to the reciprocal of the base. So it's 1 over the base. So a to the exponent negative b is equal to 1 over a to the exponent b. Or if we have x over y to the exponent negative z, that's equal to y over x to the exponent positive z. So now hopefully you can explain the reasoning behind 0 and negative exponents. I know it is hard. Go over it. It's weird. Practice it. Spend a lot of time with it. It's weird. I know. If you have any questions, please reach out. This is why I am here. Call me, email me, connect with me through Facebook. Thanks so much for joining me today. Sorry it was rushed there at the end, but we had packed in a lot. I hope you have a lovely day and Mwich.